Follow the standard for this video's characteristics of graphs level 2. Our objectives include determining when a function is increasing, decreasing, or constant, locating maxima and minima of a function, determining when a function is concave up or concave down, and evaluating one-sided limits. We start with determining when a function is increasing, decreasing, or constant, and some definitions. First one is that a function f is said to be increasing on an open interval I if for all a and b in that interval, a less than b implies that f of a is less than f of b. Said another way, the function value gets larger as we move left to right. For the second definition, a function f is said to be decreasing on an open interval I if for all a and b in that interval, a less than b implies that f of a is greater than f of b. Now the function values get smaller as we move left to right. And for the last one, a function f is said to be constant on an open interval I if for all a and b in that interval, f of a is equal to f of b, i.e. the function's value stays the same as we move left to right. So we can see them in the blue, pink, and green off on the side there. The first one, y is increasing, so as we move left to right through our x values, we can see the graph going up, or the y value or function value increasing. That happens as we move from -2 to 1. Our y value or function value remains the same up at 5 as we move from 1 over to 4. And then as we move down and right from 4 to 6, our y value or our function value is getting smaller, so the function is decreasing. Note, intervals where a function is increasing, decreasing, and constant will always be stated in terms of the domain or x values like we did for the graph there. And we can do a bigger one together now. For number 1, we have the following function. Determine the domain, range, and intervals where the function is increasing, decreasing, and constant. So for domain, we're just looking from the left to the right. So left, we come all the way out to -3, and it extends over to the right to 6. Since both values are included, we can use our brackets for the -3 and the 6. For our range, we're looking from bottom to top. We bottom out here at -2, and we don't have any issues, jumps, gaps in the graph as we move all the way up to 6. So we can go for our range from -2 up to 6. To see where the function is increasing, we want to still work left to right through those values. I think we had blue there, so we can try and stick with it. We can see as we move left to right from 3 over to 5, the graph is getting bigger or going up as we move to the right. So we're increasing here from 3 to 5. For the increasing, decreasing constant, I didn't say it, but I did it. We're always going to use parentheses. We can't increase or decrease at a point, so always open for those. For our constant here, we can see from -1 over to 3. I took constant even though we had decreasing there. So for decreasing, we have a couple. We're going from -3 out here all the way on the left until we get to -1. And then again, comma or union. Some books will use either. I don't care which one you use. As long as you say that we have both of these intervals. The other one goes from 5 out to 6. We've got our decrease over there. And I tried to draw everything on that x-axis so we could see that everything in our domain is doing something, either increasing, decreasing, or staying constant. So we'll see that even with some gaps for like piecewise functions. All right, next we look at maxima and minima of a function. For our definition, a function f has a local maximum at c if there's an open interval I containing c such that for all x and I, f of x is less than or equal to f of c. The value f of c is called a local maximum of f. Definition, a function f has a local minimum at c if there's an open interval containing c such that for all x and I, f of x is greater than or equal to f of c. And that value f of c is called a local minimum of f. So we can connect some pictures to the words. If we've got a hill and we had some value c with a function value of f of c. That's where we'll have our local max. So we're looking for a hill or a peak. For a local min, we're looking for the opposite. At some value c with a function value of f of c, we would have a valley. Right, so that function value f of c is smaller than every other value around it. And if we do have a nice polynomial function, which we'll look more at later with some terms in it, we can label a, b, c, and d, and their corresponding function values, f of a, f of b, f of c, and f of d. If we do look at little intervals around them, right, around a, or around b, around c, around d, if we extend out to the function values there, we can see they are the highest for the local max, respect lowest values in those little intervals. Right, so we have local maxes up here at f of a and f of b, and local mins, or f of c, sorry, and local mins for b and d. But we're just looking for those peaks and valleys as we move through the function. Definition here, a function has an absolute maximum at c if for all x in the domain of f, f of x is less than or equal to f of c, and that function value, again, f of c, is the absolute maximum of f. Another definition, a function of f has an absolute minimum at c if for all x in the domain of f, f of x is greater than or equal to f of c. And again, that function value f of c is the absolute minimum of f. So the difference there is between us just looking on an interval localized around the point, like we drew in the purple for a, b, c, and d, versus for the entire function and the entire domain of the function. So the one I drew that has an arrow going all the way down left forever and all the way up to the right forever there would have no absolute minimum or maximum, since the function keeps going in both directions forever. We'll look at some examples below that do have some. We start with a little theorem here that you'll see more of in calc, but the extreme value theorem states that if f is a continuous function whose domain is a closed interval, a to b, then f has an absolute maximum and an absolute minimum on a, b. So if we do have a continuous function on the closed interval, we're guaranteed to have a max or min. It's either going to occur at one of the endpoints or at some peak or valley in between. For 2, we'll look at a couple of them. For each graph of a function, find the absolute maximum and absolute minimum if they exist, and identify any local maximum or local minimum values. So we'll write out the local first, since we just did a little example with them. Our local min, we can see there's an interval around 1, where we have this lowest point, right? We see that valley there. So we say that we have a local min of 1 at x equals 1. So the minimum value is the y, or the function value. Where it occurs is at the x value. For a local max, we're looking for a peak. We have a peak at 4, or of 4, at x equals 4. For our absolute min, we can see that absolute minimum of 0 at x equals 5. So now we're looking for that whole domain here. And since our domain only goes from 0 out to 5, we see that lowest possible point on the entire graph at 5, 0. And our absolute max is 4 at x equals 4 still. Definitely common for our local and absolute max to maybe be the same, depending on which direction the graph opens. We'll do more with them when we see the polynomial functions and other types, but for now we can see that's the highest point on the entire graph. Nothing goes above that value at 4. All right, for b, we don't have a continuous function, so it's going to be a little different. We can see holes at 2, 4, and at that endpoint, 3, 2. So if we are looking for a local min, We don't see anything. There's no values here. We can't take the endpoint because there's nothing to the left over here, right? We need an interval around the point. There's no interval around 0 because the function doesn't exist to the left of it. We do see an absolute min as I go out of order, but so I'm talking about that point of 1 at that point, x equals 0, right? It's the lowest point on the entire graph we're given. For the local and absolute max, we have none for this function. Absolute down there. We can see what looks like a peak, but because we have a hole there, we never actually hit the value of 4. You can see both sides from left and right are getting really, really close to 4, but never actually touch. So there's no highest point. We can always get closer to that hole, right? Infinitesimally close. For C, we've got a little more we can work with. For our local min, we can see that valley at 0, 2. So our local min is 2 at x equals 0. For our local max, we can see a peak up at 2, 4. So it would be 4 at x equals 2. For our absolute min, you can see hopefully that arrow extends down forever along x equals 3, right? What we have called a vertical asymptote, which we'll view more with the graphs. But we would have none there, right? That graph continues down forever. But for an absolute max, since the other side does end at that point -1, 3, our highest point for the entire domain of the graph is at 4, or is 4 at x equals 2. So same as our local max. All right, for concavity, we're looking for concave up and concave down. Our definition here, the graph of a function is said to be concave up on an interval I if the graph lies above all of its tangent lines on the interval, and we'll draw some on our picture below. Definition here, the graph of a function is said to be concave down on an interval I if the graph lies below all of its tangent lines on the interval. And so we can see that with the pictures here and kind of call back to that difference quotient where we looked at the secant line versus the tangent line. But we can see all our tangent lines to the curve, if I can draw some kind of right here. Right, all these tangent lines would remain below. This would be our concave up. Really, we're looking for a cup shape. And then for the other one, for the graph to stay below all of its tangent lines, we're looking for that frown or that concave down. All right, so the note says what we just said. For concave up, C up, we're just looking for a smile or a cup shape. For concave down or C down, we're looking for a frown or a hill, right? So it's open and down. So let's try put it all together. 3, for the graph of the function below, we're going to determine domain, range, local, and absolute max and min values if they exist, intervals where the function's increasing or decreasing, and intervals on which the function is concave up or concave down. And then we'll talk about a definition we forgot to put in, but where we change concavity. So our domain, if the graph extends up and to the left and up and to the right off the graph, we're assuming we've got those arrows there that are sending us forever and ever and ever out to the sides as we go up. So our domain is all real numbers, or minus infinity to infinity. Infinities always get those parentheses because we can never actually reach those values. For our range, we can see our bottom over here at -27, and then it goes up forever. So our range, we got to include that -27 value, and then we're going off up to infinity. For our max and min, we can see that we don't have any hills, and the graph goes up forever, so we definitely have no absolute max. What could look like a local max, this point at 0, 0, if we do open an interval around it, we can see to the left we're going above the point, and to the right we're going below the point, so it wouldn't be a maximum or a minimum. And then all we have is that valley at 3 minus 27, so we have no absolute max. We also have no local max. For the minimums, we see a local and absolute min of -27 at x equals 3. Right, we've got that 1 point that is our valley. It's the lowest on the entire function, right? It was the bottom of our range. And if we do look at a little interval around 3, it is the lowest point in that interval. Doesn't matter how small we draw that interval, we just want to see it the lowest on that little point, so lowest in that valley or lowest in that interval. For increasing, we're looking for the graph to move up as we go to the right. We can see that happening from that valley at 3 off to infinity. For the function to be decreasing, we're coming down as we move to the right. That's that whole left side of the graph from -infinity all the way over to 3. For concavity, we're looking for a cup up or that cup down. We are concave up from -infinity all the way until we get to 0. And then we can see those tangent lines start to go above the graph instead of below the graph. Right, so on the right side is 0 until we get to 2, we're concave down. And then at 2, you can see with kind of your hands, if you put them together, your left hand could be cupping down, your right hand cupping up, and your fingers would come together at 2 there. So we are concave up again from 2 to infinity. All right, and the definition we do want to add in is that for an inflection point, we'll keep it as easy as we can. An inflection point is a point where the function changes concavity. So where we jump from concave up to concave down or concave down to concave up, we have inflection points on this graph at 0, 0 and to -16. All right, so we want to look where those cup up and cup down shapes come together, or where we change concavity. And for our last objective, we've got one-sided limits, and we can talk about limits and infinity and asymptotes a little bit, and we'll touch on them way more when we do the graphing sections. But recall, in calculus, we'll talk about the limit of a function. To stick with less formal definitions, we can say that a function has a limit at a point if, as we zoom in around an x value, we also zoom in on a single y value or function value, i.e. we approach the same height as we get close to an x value from the left and right. A note here, we can say that a function has a limit from the positive side or right side at a point if, as we zoom in on the right side of an x value, we also zoom in on a single y or function value. We write the limit as x approaches a from the right, that's the plus, or from the positive side of f of x. We can say that a function has a limit from the negative side or left side at a point if, as we zoom in on the left side of an x value, we also zoom in on a single y value or function value. We write the limit as x approaches a from the left of f of x. So we're going to use the graph below to look at some one-sided limits and some refresh of limits from the earlier standard. But we've got our graph here of f of x. We want to look at the limit as x approaches 0. I think we want that one to be from the left. It looks like we missed the negative there. So as we approach from the left, we're coming in from the left side towards 0, and you can see we approach that single height of 1. So this would just be 1. As we approach 0 from the right, we're coming along this piece of the function, but it's also approaching a height of 1, so we can put a 1. Should hopefully match up with what you looked at in one of the really early standards. Our limit as x approaches 0 is just 1. Right, if both sides closed in around the same point, we had a limit at that value. And f of 0 here is also 1. And so what we can highlight here, and you'll do way more with in calculus, this is our definition of continuity. Right, so we could say f of x is continuous at x equals 0. So for our limit to exist, left and right limits have to be the same. If the limit value and the function value both exist and are equal, we're continuous at that point. We can look at -1 as we approach from the right. As we come in from the right, we're coming down this piece of the function to a height of 0. As we approach from the left, we're coming in from the left of -1. We're running along this piece of the function to a height of -1. And so we can see that jump discontinuity that's been talked about before in class. So we do not have a limit as x approaches -1, right? The limit does not exist there because we come to different heights on both sides. And so f of -1, we can see that closed point or that defined circle down at -1. So we wouldn't be continuous there, and we've talked about that before, again, as a jump discontinuity. Next one we want to look at going out towards the infinities. So as we run out towards positive infinity, this dashed line is what we call a horizontal asymptote. We can see the function is just going to run out and get really, really close to, but maybe never touching 1, but it's going to stay really close to 1 as we move out towards infinity. So as we move out towards positive infinity, we stay close to a height of 1. For negative infinity, we're looking left down our number line. We can see our function value is going to kind of level off right around a height of 3. So our limit as x goes out to negative infinity would be 3. And then we're looking at -2 from the left and right to finish this one off. As we come in from the, I think we did right first for the other ones. Is it still right? Yeah, we'll do the right. So to the right of -2, we're coming in from that positive side. We're running up along this piece of the function and up along, we'd call this vertical asymptote at -2. And our function value is going off towards positive infinity. We're going to write infinity for our value and then make sure to note our limit does not exist here. The infinity tells us it increases without bound, right, at the vertical asymptote. And we can see a similar thing happening as we come into -2 from the left. So as we approach from the left side, we're running down along this piece of the function, along the left side of x equals -2. And so we're going down towards negative infinity. So we'll put that for our answer. And again, note the limit doesn't actually exist here because infinity and negative infinity are not numbers. Here, the minus infinity tell us the function decreases without bound at the, I'll just put VA here for vertical asymptote. All right, so we'll do more. We'll look at the graphs a lot again in class. And when you get to calc, you'll tie some of the algebra to it more to actually solve for the values. But here we just want to get you looking at them again, kind of back to reading that graph. So try the ticket, come with questions.